So we're here for round-off error. What I've got is my IDE, my Integrated Development Environment open. I'm running a Mac, right? So this is Xcode. And you'll notice this program is in C++. Again, you don't have to program in C++ to know what I'm doing. I'm going to try and explain it all to you. But what I want to do is to demonstrate, basic round-off error. Everyone, all of you, excuse me, normally think of computer programs and the computer as having no error, right? It's never going to have a problem. Most of you are probably too young to remember when Windows had its lovely error where you could take 1, subtract 1, and it actually gave you a number instead of 0. In this particular case, though, what we've got is sort of a test, excuse me, for how much round off there's going to be. What this is a sum of 1 over n, right? 1 plus 1 over n. And of course, as n gets bigger and bigger and bigger and bigger, this should go to just 1, right? Because 1 over n should go to 0. So what I've got is a floating point notation and a double, which is double precision, double a float point value. And I have two sums, and I have two terms, a term and an n value that I'm going to mess with. And then I'm going to put it through a loop, and it's going to just add all this up. It's going to take the sum, add the term value to it, 1 over n, whatever n happens to be, and then add that back to sum. And as n gets bigger and bigger and bigger and bigger, then this is going to get to be closer and closer and closer to 1. What I'm going to do is I'm going to start off with a value which is 99. And here, notice this plus equals. That's a shorthand way of writing sum equals sum plus term. Here I've got sum2 equals sum2 plus term. If I could just shorthand write it, I can do that. And of course, count plus plus just means add 1 to count. And it's going to output down here on the bottom sum and sum2. All right, now remember, sum is a floating point value. Sum2 is a double precision value. It's double float, so it's double the number of digits. All right, so I should get more precision with double. So if I start at n equal to like 99, right, and I just run this thing, it tells me build was successful, and then it just goes through and runs it. The hello world is just there, so I knew that I was getting the output I'm supposed to be getting. It's not, anything spectacular. Notice that the sum and sum2 are equal for that very low value. All right, now change n, and I know I should make the program interactive, but I'm lazy. Change it to like 150, all right, and then rerun the program. Tells me build was successful. Now look at sum. All right, sum has gone to 0.999999, but sum2 is still 1. All right, so I'm getting the correct answer here. Here I've got round off. All right, I am definitely getting round off in that term. If I push this to an even larger n, that's 9,999, right, and I rerun the program, now sum has overshot the value I wanted. Right, I'm bigger than 1. Now, true, that's tens, hundreds, thousands, 10,000s, 100,000s, 6/100,000ths over. But if I'm looking for a high precision answer, that's not going to cut it. That's going to give me the wrong value. So I can't have that. Notice my sum2 is constantly coming out as the correct value. All right. But double precision values take up more memory space, more RAM. All right. So people tell you don't use them unless you absolutely have to use them because it takes up more RAM. With all our computers today, which have a gazillion amounts of RAM in it, it shouldn't matter really. But now what I'm going to do is I'm going to push n to an absurdly large number. I'm going to add 2 more 9s. Right, so this is 999,999. And now I'm going to run it. And now it gets worse. Now sum has an error in the thousandths place. Sum 2 is still fine. This has got an error in the thousandths place. And now I'm overshooting by 0.009. That's good enough to call it 0.01 off. If you were going to round this off, that's absolutely going to get you an unacceptable answer. And if you turn this in to somebody who you're doing work for, who's paying you, they're going to have a bird fit if you are off by that much. I mean, that's 9 parts in 1,000. Right. So for high precision, this is really, really bad for very high values. If I push this to really, really add 2 more 9s to it, and then I rerun this. All right. Sum has just tanked. It went and flipped in the totally opposite direction. All right. Granted, this is 99 million now, but you take a look at that, and that 0.25 is not even close. Now you've got 75 parts in 100 error, is what that's telling you. So anything which is being done a lot, and anything which is being cranked out is just going to give you terrible results. So this should sort of, what I'm trying to do is drive home the fact that you want high precision, you have to check your computer. It used to be when we had computers out there that were 486s and first generation Pentiums, and we had Macs, and we had everything else, and we had Linux and new versions of Linux all over the place. Not only did you have to take a program like this and run it to check the chip to see what kind of error it was giving you, you had to check the operating system to see what kind of error it was giving you. This is always a good thing to have in your toolbox. Just carry around something really, really simple, right, with a compiler. Right, just compile it and run it on the particular computer, right, or the system that you've got to see what it is doing to you. And how far you can push it before it's going to crash and burn. Like, this is definitely a epic fail. Your answer is supposed to be 1, and this thing is coming out as 0.25. So there we are. That's my piece. I hope I have productively added to your other videos that I have listed for you to watch.